4.7 deals with inverse trig functions. So earlier in the semester when we looked at inverse functions, right, we said an inverse function is the original function reflected over the line y equals x. But in order to get an inverse function for something like a quadratic, we saw this on exam, I think it was exam 2, we saw that we had to restrict the domain, because if you try to flip a parabola, it wasn't a function anymore. And the same thing's going to happen with the sine and cosine wave. So one of the things we want to do here is we want to sketch these inverse functions and also get their domain and range. So the range of a normal sine wave is -1 to 1. We said the graph never goes above or below those values. So that is going to be the domain of the inverse function. So that is true for both sine and cosine. The range, however, is going to be different because the domain of a sine and cosine wave is all reals, but the range cannot be all reals because we have to restrict the domain of the original wave in order to graph it. So for inverse sine, I'm going to go back to my sine wave to show you why we restrict where we do. If we go to the graph of sine, right, well, from -1, right, to negative or to +1, when we look at the range, we see that those are turning points, right? The graph is about to turn down, and so if I flipped it, right, just like with the parabola, we would lose its classification of being a function if I flip the whole wave. So the sine wave oscillates around the x-axis. If I flip the whole wave, it would oscillate around the y-axis and it would fail the vertical line test. So we trim it at one of these turning points and these turning points, and that's what we graph. So for a sine wave, we crop the function at -π/2 and π/2. So if that's the restricted domain, then that means the range is going to be -π/2 to π/2. On a cosine wave, because it's slightly shifted, we trim it here at the first turning point, and then we trim it again at the second turning point. So the range here is 0 to pi. Now keep in mind, there are multiple ways you could trim cosine and sine in order to get an invertible function, but we want to have the biggest piece of the wave we possibly can. So that's why we trim it at the turning points where we do, and we end up with these values. So now let's see what these graphs would look like. So if I draw an XY plane, and now on the x-axis I put -1 and 1, and on the y-axis is where my angle measures go. Over here I'm going to have -1 and 1, but notice the range here is 0 to pi, so I'm going to label pi and π/2. So with inverse functions, the x and y coordinates switch. So if sine of 0 is 0, well then when you flip those values, you still get 0, 0. So that point stays fixed. But sine of π/2 is 1. So that means if I plug π/2 in to the sine function, I get 1 out. But if I plug 1 in to the inverse sine, π/2 comes out. Similarly, the same thing happens with -π/2 and -1. So when I draw these functions, I sketch it like this. So one of the questions that I get commonly asked is, how do you know how to turn the function? Well, the way I know how to do it is if I've drawn this right, if I completed the wave, which I'm going to do with like a dotted line, right? You can see that when we curve it like this, the wave wants to oscillate around the y-axis. So this is what it would look like if we turn the whole wave, right? But only the solid piece is on the inverse function. For cosine, well, cosine of 0 is 1, so inverse cosine of 1 is 0. Cosine of π/2 is 0, so inverse cosine of 0 is π/2. And then inverse cosine of -1 is going to be pi. So now, when I draw this wave, it turns like this. And I can see that if I tried to complete the entire wave, you can see that it would also look like it wants to oscillate on the y-axis, but only the solid part is the correct inverse. So whenever we talk about inverse sine, inverse cosine, these are the domain and ranges that we use by default. Tangent's a little bit different. So tangent, when we graphed it, looked like a bunch of S's repeating over and over again. So the domain of tangent was all reals. So now the range of tangent is all reals. But tangent had vertical asymptotes at every multiple of pi over 2. So this time what we're going to do is we're going to restrict the domain of tangent where we're only taking the one permutation of it right around 0. So we only go from negative pi over 2 to pi over 2. And on the domain, notice that those values are not included because on a tangent graph, it's not defined at pi over 2 or negative pi over 2 because cosine would be 0 at those places. So tangent doesn't exist there. So this is how we restrict the domain of an inverse or tangent to make it invertible. So the graph on tangent, it looks like this, right? It goes vertical up and down. So that means when we flip it, it's going to want to follow the x-axis. So negative pi over 2 and pi over 2. Oops, I am so sorry. Some of you were probably screaming at the screen. I wrote these in the wrong places. Angles go into tangent, they come out. So I wrote these backwards, y'all. There we go. I also put brackets around those infinities. That was a terrible thing to do. All right, so the angle measures, once again, go on the y-axis for inverse trig functions. And there's our positive infinity, negative infinity. So if pi over 2 and negative pi over 2 were vertical tangents on tangent, right, then they've got to be horizontal tangents on the inverse. So we have horizontal tangent lines, horizontal asymptotes. Sorry, y'all, I've been teaching calculus all day. Horizontal asymptotes. So the graph that normally went like this now flips and looks like this. So tangent of 0 was 0, so inverse tan of 0 is 0. As you got closer and closer to pi over 2, the graph climbed up to infinity. So now, as your x values approach infinity, the y values are getting closer to pi over 2. On the original tan graph, right, as we got closer to negative pi over 2, the graph went down to negative infinity. So that means as you get closer to negative infinity in terms of x, the y values are getting closer to negative pi over 2. So just like any other inverse function, we had the property that if you composed a function with its own inverse, you got x, right? And if you plug the inverse into the original function, you would also get x. But this is only true on the domain, right? If the domain was all reals, this was true everywhere. But if you have to restrict the domain like we did here, this property will only hold on the restricted domain. And we're going to deal with that in a little bit. So a very common mistake students will make on exams is if we give you these variables, but the value of x is outside of these values, we have to use a different method. You cannot assume that sine always wipes out inverse cosine. It's only true when x is here, okay? So we have to make sure, and then notice the values change when you reverse the order. So we're going to show you in some examples how to deal with that